having looked at linear search, we might ask ourselves, is there any way to do better than order n in doing a search through an array? Now that might seem crazy because it seems like in order to know for sure that something is not an array, certainly you must have to look at every element. And while that's sort of true, you can actually do a little bit better than order n if you know something about your array beforehand. And that's the basis of binary search. Binary search is a very fast way of searching through an array, but it depends on knowing one critical thing about your array beforehand, and that's knowing that your array is already sorted before you begin. If you know that your array is already sorted before you begin, you can play a game that's a little bit like the number guessing game. Like if you've ever played a guessing game where you say, pick a number between 1 and 100, and you say, is it higher or lower than 50? And if they pick the number 80, they'll say higher. And then you guess between 50 and 100, and you say, is it higher or lower than 75? And they say higher. And then you guess between 75 and 100, and you say, well, what's between 75 and 100? It's about, what's 80? Is it higher or lower than 87? And they say lower. And you continue splitting that difference until you get to the particular element that you're interested in. That would be a kind of guessing game that you might play. But binary search does that formally through an algorithm. Again, assuming that the array is sorted in the beginning. And so in contrast to linear search, when given an array and given an element that you're looking for, you don't start in the beginning and go through the entire array looking for things that are in that array. Instead, you start in the middle and you ask, is this the element that you're looking for? Maybe you got lucky. And if it's not, then you continue your search only in the upper or lower half of your array. And in this way, you're doing a divide and conquer strategy, much like merge sort or much like quick sort. And it's that divide and conquer strategy which gives you the increased efficiency. Now, because you're going to split the array in the middle and do the search again on the higher or lower half, well, this ends up being a recursive strategy as well. So binary search is bringing together a lot of different things that we've looked at. The idea of sorting, the idea of recursion, and then the idea of search, which we're kind of building on right now. So each step in our search process, the search is cut in half. So here's an example of what that might look like concretely. Here we have a bunch of examples of an array that's in the blue-green here, and you can see that it's sorted and it's got a bunch of numbers in it. In this case, numbers between 1 and 32. And we're imagining that our user wants to see if the element 15 is present in that array. And so that the way that we do that is a careful management of the index versus the value in the array. So we're going to use the indices 0 through 9 to find the middle element. And that middle element is going to be element 5. And so we're going to look at that middle element. Oh, sorry, we're going to say it's the element is index 4. And that value at index 4 is 9. Now we know 9 is in our array, we know it's in the middle of our array, and we know that we're looking for 15. So now we decide that we're going to look just in the upper half, in indices 5 through 9, because we know that if 9 is present, it's got to be there, because those are all higher than what was in indice 4. Well, now in the middle of that upper element, we look at position 7, and we look at what's in position 7. We see it's 20, and that's higher than 15. And so we decide to recurse on the piece of the array that's between the last thing we looked at, the middle element, and the element that we just look at, indice 7. That consists of 12 and 17, so we've split that in half as well. And we look to see whether or not it's at position 5. It's not at position 5, so it must be higher. We look at position 6, and we see that it's not present. But since there's no other place that we can look in our array, we've bracketed it. 12 is below it, 17 is above it, and those are adjacent. And so we know, therefore, that 15 must not be in our array. And so we return a signal indicating that it's not present. And again, we'll assume that that signal will be returning -1, and we'll assume that our array only contains positive integers. So this splitting strategy is what gives binary search its power. And what I want to do is I want to walk through an example of the code in Eclipse and show you how that works using the binary searcher code here. And here, let's take a look at that before we look at the runtime of it. So here's our demo. This is our driving class that's present. And what we're going to do in our demo is we're going to, for the purposes of running our example, we're going to create a random array with 20 elements in it that contain integers between 1 and 100 chosen randomly. Then, because binary search requires our array to be sorted first, we're going to sort that array here in line 14. So that we can see what's happening, we'll print it out, and then we'll proceed to do a user interface loop where we ask the user for input, or we're going to create a scanner. We'll have a sentinel called done, that as long as that is not true, we'll continue asking the user for input. We'll ask the user for what they want to search for and a -1 to quit. We'll read that in. As long as they haven't asked to quit, we'll go ahead and we'll then run our search algorithm and we'll print out whether or not we found it. Now look at how our search algorithm is called. Our search algorithm is given first the array that we want to sort over, that was created up here. Then it's given the starting position. Well, if we're searching over the entire array, that starting position is going to be 0. But the reason why we're passing that in is because this is a recursive method, and it'll be called again with different indices. And then the highest index we want to look at is the length -1, because of course we're using a 0 indexed array. And then finally, we'll pass in the thing that we want to search for, position n. Now, if we go to look at that method, I'm going to highlight that method and then hit F3 in order to jump to that definition of that method. That's here in binary searcher. You can see that this recursive method, a static call, takes in the array, the low, the high, and the value. And then it does the recursive work. Well, first of all, it checks for to see what the base case is. The base case is that if the lower index is not less than or equal to the higher index, then we're going to do our search. But if it is, then we haven't found the element and we return -1. So that's our base case. Any recursive function needs to search on a smaller problem, and it needs a base case in order for it to work. If it's not the base case, then what we're going to do is we're going to find the middle of the indexes, all right, of the indices. So we're going to use integer division. We're going to take the average of the low index and the high index, but we're going to do integer division. So what we're going to get back is an integer. How do we do integer division in Java? Well, we just make sure that the two things that are being divided, the numerator and the denominator of our division, are integers. The result would be an integer. We don't use a special operator. Python uses a special operator. Once we have the index of the middle, that's mid, we're going to go ahead and look at what's stored there. And if what's stored there is what we're trying to find, then we just go ahead and return the position, not the value, the position at which we found that element. Oh, I guess that's actually why we're returning a -1, because the -1 indicates the index, not the value that we found. Okay, so that was a mistake I made. So we're going to return the position, the middle position at which the value is found. And now, if we didn't find the value at the middle position, we'll check to see, well, is the middle position less than our value? Is the value stored at our middle position less than the value that we're looking for? If so, we're going to look at the upper half of the array. We're going to recurse on the upper half. And we'll just return whatever the search on the upper half returned. If our value is lower than what is in our middle point, then we're going to search on the lower point, going from our existing low point to one less than our middle point. And we'll continue getting smaller and smaller and smaller until either we return a -1, indicating that the element's not present, or we return the index of where the value is found. It's kind of a beautiful little algorithm. So let's go ahead and let's use debugging, and let's step through and see this working. So I'm going to put a breakpoint at line 13, and I'm going to run this I'm going to debug as a Java application. Go ahead and hit OK. We'll go ahead and start the running process, and we are running, and I'm looking at my console, and you can see that we've stopped here at line 13. So I'm going to step over that and step over that. My hotkeys aren't working. Okay, so I will step over that. And we can see up here what got stored in A. It's an array of 20 elements, 0 through 19, and you can store it contains 96 and 11 and 45 all the way up to 35. Super. So now we're going to sort that array, and now you can see that A has changed, and now it goes from low to high. Keep going. We'll we'll output that array, so we see what was in our debugger, pass that to the user, create a scanner, create a sentinel. As long as our sentinel's as long as we're not done, we will ask the user for input, and then we'll get input. And we'll say, let's search for element 22. Let's search for element. Yeah, let's search for 22. Okay. The user did not ask to quit, so we're going to go ahead and do our search. Now I'm going to step into this binary searcher. Now notice we're passing in the entire array, starting at position 0 and going to the 1 minus the length, looking for n. And if we look for what n is 22, the value up here that the user indicated that they were searching for. Okay, so now we're not going to step over this. We're going to step into that. And we're going to look. Now we are in the first call to the search function. If you notice here, you can see that the stack of calls started at main, and now we're going into search, and we'll see that grow as we do recursion. So we look at what our values are. We have an array A, our low index is 0, our high index is 19, and the value we're looking for is 22. Have we met our base case? Not yet, so we're going to go ahead and calculate our middle element. Between 0 and 19, we get the value 19. 19 divided by 2 is going to be, what, 10.5? No, 9.5. And so we throw away that fractional piece, and the index in the middle is calculated as 9. Is the element at position 9 equal to 20, what we're looking for, 22? Nope, it's 44. And so we're going to have to think about what we're going to do in that case. 44, is 44 less than our value? No. And so instead, we're going to recursively search on the elements starting at low. So we're going to go from 0, and we're going to go till the midpoint, which was 9, but we just checked 9. So we'll go 1 less than that. So we'll go 0 to 8, still looking for our same value. Now I'm going to step into this function again, and we're going to see that here we've built up another recursive function call. So now we're too deep in our search. In this version of our function call, clicking here, our values of low and high are 0 to 8. If we click here, we can see that the values of low and high in that frame are 0 and 19. But we're going deeper into our recursive call, so we're at 0 and 8. So we step over this. Is low less than high? Yes. And so now our middle point is 4. And if we look at our array, position 4 is the value 24. So that's not what we're looking for. So we're going to go ahead and step over that. And we're going to check to see if what is at position 4 is less than our value. It's not. It's higher. So we're going to step over that, and we're going to continue our search on the lower piece, going from 0 to 1 less than 4, which is 3. Go ahead and step into that method now. And you can see we build up another stack frame here of our search. So we're now 3 layers deep in our recursion, and now low is 0 and high is 3. We're still looking for 22. We have not reached our base case yet, so we're going to step over that. We'll find our middle point. Our middle point between 0 and 3 is 1. If we look at A1, that's 11. That's not what we're looking for. So we're going to go ahead and step over that. But this time, 11 is less than our value, so we're going to search on the upper half of our array. So we're going to start at 1 greater than our middle point, 2, and we're going to go to our higher point, 3. Step into this method now, and we'll build up another recursive call. So we're now 4 layers deep in our recursion, stepping over that first one because we're not at our base case, figuring out what our middle point is. It's 2. We look at what's in position 2, that's 17. That's not what we're looking for either. So we're going to go ahead and step over that. Is 17 less than our value? It is. So we're going to search in our upper half. We're going to go from our middle point, which is 2, 1 more than that, 3, going up to our higher point, 3. So we're going to end up searching just one element, but go ahead and step into this recursive function call. Step into it. Is lower less than or equal to 3? It is, so we're not at our base case yet because we still have one element to search for. Go ahead and calculate our middle point. In this case, it is 3, so we get 3 as our middle point. Is the value at position 3 what we're looking for? It is. So that's going to end our recursion. We're going to go ahead and step over that true call, and what we're going to return through our recursion is the index at which we found this element, which was position 3. So we're going to return all the way through our recursive function call. So let's go ahead and step over this line. We're going to return, we come back. This is where we made that recursive function call, but we're returning what that returned. So we're going to continue returning the 3. We're going to return what that returned, continue returning the 3. And finally, we get up to our initial call that launched us, and we're going to set position equal to the value of 3. Stepping over that, we see that position equals 3. 3 is our answer. We output that we found our position, and I'll continue running this without stepping through. And now we'll just say -1 to quit, and our program ends. So a really elegant, efficient search algorithm. How can we analyze how efficient this actually was? Well, let's step through the different ways in which, let's step through the way in which we can analyze this search algorithm. So let's start by considering what the running time is of a single step, the step where we consider the middle element and then recurse. So the running time of an array of length n is going to take one visit to the middle element, that's the +1 at the end, plus whatever it takes to search over half of our array, the half that we continue going through. And the cost of that is t of n over 2. So we have a nice equation here that describes what our running time is, but it's not solved because we have this sort of recursive element in our formula, t of n over 2. Well, what is t of n over 2? Well, we can figure that out just by taking that first formula, like we did before in our analysis of quicksort, and rather than plugging in n, we'll plug in n over 2. So we know t of n over 2 is equal to t of n over 4 because n over 2 is n over 4 plus 1. Okay, well now let's take this value of t of n over 2 and plug it in here and see what our original formula ends up being. Well, if we take t of n and we plug in what t of n over 2 is, we end up with this formula where we replace this element with this formula here, and that ends up here. And so t of n is this expression here plus 1. And if we simplify that, we get t of n equals t of n over 4 plus 2. If we think about that, we could also take t of n over 4 and plug that in here and get another value, which t of 4 is t of n over 8 plus 1. And that would mean t of n is also equal to t of n over 8 plus 3. And that gives us a general form of our equation. It says that our general form, t of n, the running time of t of n, is equal to this recursive element t of n over 2 over k, because each time we increase that, we go up by a power of 2. And then we add 1 for each power of 2 we go up. So our general formula is t of n over 2 to the k plus k. Okay, so now let's make an assumption about how long our array is. Let's make an assumption that the initial length of our array is a power of 2. So our original array maybe is 16 or 1024 or some power of 2. And so we can say that n is some power of 2, 2 to the m. And we can solve for m and say that the value of m is log base 2 of n. That's just solving for m in this formula here. But now we have some nice values that we can plug into our equation here. And we could say that t of n, therefore, is going to be equal to 1 plus log base 2 of n. Why is that? Well, that's because our value here in the numerator n is, we know, is 2 to the m. And we know that our value here is 2 to the k. And so if we assume that m and k are the same, because the number of times we can split is going to be the same as m and k are going to be the same, then we get this value is t of 1. T of 1 is 1. We know that if it's length 1, all we have to do is look at that one element. So that's where we get the 1 from. And then the k here is driven from right here, k and m being the same, therefore this is equal to log base 2 of n. And so overall we get that the answer to t to the n is 1 plus log base 2 of n. Using the way that we evaluate efficiency, we find the highest growing term, that's log base 2 of n, and we throw away any constants, and so the base doesn't matter as a result of the way in which all logs are related by a constant. And so the running time of binary search is order log n. That's great because it means that as our array gets larger, our running time doesn't get larger at the same rate. It goes up as log base n. So if we if we double the size of our array, it only goes up by order log base 2 of 1. So that's a great outcome. It means that we can very efficiently search, provided that our initial array is sorted. And so that gives us a design question that we have to answer. And that is, should we spend the time sorting our array before we start doing binary search? And how do you do that analysis? Well, we've seen that a linear search is order n. That would be appropriate if your array wasn't sorted. We know that the time it takes to sort an array at best is n log n. So how do we make our decision? If we only want to search through our array one time, then it makes more sense to do a linear search and bite the bullet of the order n running time. But if we're going to make lots and lots of searches, then it makes more sense to sort our array first, which takes more time than a linear search, takes order n log n time, but then each subsequent search becomes much, much faster. So the question in deciding how to do a search of an array, of an unsorted array is, do you want to incur that high upfront cost of sorting your array first so that your subsequent searches are faster, or do you just want to pay a medium price of order n to do a linear search at the beginning? Understanding the time it takes to do these different kinds of searching algorithms is important to make sure that the ultimate program that you write is as fast and as efficient as possible. Because as you start sorting and searching very, very large arrays, it starts to impact the running time and the kind of things that you can do with your algorithm. Great, that's binary search. Thank you for your attention.